Hello. Um, Yesterday we discussed about the levitation of a spherical object, and in session 2 we discussed the levitation of a flat plate. So we have observed that when the shape is changed, then everything from the starting from the design, analysis, fabrication, controller design, parameter evaluation, each and everything has been changed when shape is changed. So we discussed that for a particular shape of object and for a particular weight of the object, the prototype is fixed. And we discussed that there are three type of electromagnetic levitation is exist till now. So currently maglev trains that are being run on a limited basis in Germany and Japan. So this we discussed about some other applications also of electromagnetic levitation, application in frictionless bearings, maglev vehicles, induction melting, sensitive machinery, etc. We can use the electromagnetic levitation. So we discussed many applications, but rather in case of induction melting levitation, it will lead to savings in material thickness and hence cost of expensive refractory linings on the inner walls of the furnace. That is the advantages. So we have seen that there are many applications in electromagnetic levitations, and we have seen that there are three type of electromagnetic levitation exist. One is electromagnetic attraction type levitation, second is electromagnetic repulsion type levitation, and third is superconducting magnet. Also we can generate electromagnetic levitation. So in attraction type electromagnetic levitation, the coil attract the platform. So the attractive force is generated through the coil, and in repulsion type levitation, repulsive force is generated. Using repulsive force we can levitate the object. So the two different type of properties and two different type of technologies exist, and third technology is most recent, it is coming, that is the superconducting magnet. That it is very costly because it is applied in the track. So track is very costly. Okay, so these type of applications we have discussed, and to design or fabricate a prototype we require these steps. First steps was that to selection of the object, selection of the shape of the object, selection of the mass of the object. Then second step was to design the coil design is connected with the object. So there should be very good relationship between the coil and the object. Second step was the mechanical structure of the setup. So that should be true mechanical zero and spirit level accuracy setup. Third was electromagnetic analysis, that is called FEM analysis. Okay, finite element method analysis. So that we can do using analysis softwares like ANSYS simulation we can do, because simulation is important for the parameter estimation. Okay, second, then what we have to do, system modeling. So for modeling purpose there have many softwares like MATLAB, okay, Simulink, Scilab. These type of softwares is available for modeling purpose. And then and fabrication. Okay, so to fabricate the prototype, we need AutoCAD drawing. So for CAD drawing we need AutoCAD software, and then the conducting parameters of evaluation experiments. So to test the evaluation to bring the parameters, we need ANSYS softwares. Okay, and then parameterization is done. Now modeling and stability purpose. So for modeling and stability analysis we can use MATLAB, Simulink, and Scilab. and then controller design and feedback sensing. So for controller design we can use uh, we can use uh, Scilab, okay, PSpice, no, sorry, PSpice, and we can use 1 second. Okay, PSpice and SQL. Okay, so Orchid, PSpice, and SQL we can use for the uh, circuit design. Okay, then controller design has been done. Now circuit has been fabricated in board and breadboard, etc. Then last step we'll have to use the we'll have to fabricate PCBs. For PCBs, they have a very good software, that is Express PCB. By using these PCBs, uh, we can do all the circuit design. So again, I am telling, for FEM based analysis, we need NC software. For system modeling, MATLAB, Simulink, okay, Simulink, and Scilab, okay. This softwares we require. And for FEM based and for system modeling we already done, and for controller design and feedback sensing we require that PSpice, SQL. Okay. And for design and test associated circuits we require the software is the Express PCB for designing the uh, circuits. So these steps again I am repeating, to design so for FEM based analysis we require the NC software. For system modeling we require MATLAB, Simulink, and Scilab. For stability purpose we require same MATLAB, Simulink, and Scilab. And for controller design and feedback sensing we require PSpice for circuit design, okay, electrical circuit. So we need PSpice and SQL. And last step we require for PCBs, we require the Express PCB. These type of software 6 and 7 softwares are required to complete the full prototype. Okay, so this we required. Now I am going to the uh, where we end yesterday. So you can see, yeah, this we have completed. Now this, so so we have discussed that for spherical object, the shape is spherical, so center of mass is equilibrium point, so symmetric object. But for asymmetric object where center of mass is not the equilibrium point, like plate, flat plate or C-type plate, at that case complexity arises. For spherical object we require the I-type core, and only Z direction control is sufficient to make the system stable. But for asymmetric object like plate we require C-type object core, and we require 3D freedom control, like we'll have to control X direction, Y direction, Z direction. We have to taken care of roll PGO also, we have to take care. So complexity arises. So to make the system stable is easier for spherical object, okay. But for analytical model, spherical object is difficult, okay. So this type. Now we will discuss about what is the difference, what would be the design differentiation will arises when shape is changed though mass is same. Here you can see in figure 140 and 141 the mass of the object both are same 148 gram, but shape is changed. Here coil is also same coil has been used, same coil for both the setups. Mass of the object is also same, but the shape is changed. Now we will see how what change is come when shape change. You can look at this table, that spherical object, flat plate and C type plate. So three type of experiment parameters are there for spherical object, flat plate and C type. So spherical object case, the mass was 62 gram, flat plate the mass was 148 gram, C shaped plate mass is 148 gram, and levitated force means mg, that is 0.6 newton, 1.45 newton, 1.45 newton. So coil will be designed from the levitated force, how much force we require, and from that point, from there we'll start the coil design. So once the coil is designed, object is ready, setup, mechanical support is ready, then we can start the parameter evaluation. And then when if we get the parameter evaluation, then we can do small signal model, means we linearize the model at a particular operating point, and operating point will be chosen from the inductance plot, where the inductance is almost constant. At that point we will take the operating point. At operating point we will take all the uh, operating parameters, and that parameters we will put in the linearized model. And after getting the linearized model, putting the parameters at the operating point where we have linearized, at that point actually we have linearized. So at that point we have linearized the model, so we will get the transfer function at that point only. So the controller will operate only that point, operating point. So it's a small signal model, it will not work in each and every point. Okay, so it's a small signal model. So we have received the operating point from the inductance plot, and we have received all the operating parameters, and we have put all the parameters in the linearized model, where the non-linear model has been linearized at that desired operating point. Okay, and operating point is taken from the inductance plot. Possible constant zone we have taken that point. And now all the parameters are shown here: electrical parameters, mechanical parameters, and then controller also shown in this table. So for spherical object only one loop was there, okay, only lead compensator. But for flat plate they have two loop. In the inner loop they have the current controller, PI controller, and the outer loop there was the lead compensator. For the C shape also there was inner loop there was a PI controller, and outer loop there have a lead compensator, that make the system stable. So we have observed the stability analysis, frequency analysis we have done, and we have received that gain margin of the overall system is 55.2 dB for the spherical object, 56.4 dB for the flat plate, and 57.9 dB for the C-shape plate. So closed loop gain margin of the overall system. So with controller the gain margin is this, so 60 dB. So all the, and we can check the open loop poles. There was a unstable pole at unstable pole at 14 for the spherical object. One unstable pole is there. Okay, so open loop system was third order system, electrical system was first order, and mechanical system was second order. Overall it's a third order system, and in that third order system one right hand side pole was there, open loop. Now please see, with controller closed loop poles are shifted in the left side of the S plane, so no unstable pole in the right side of the S plane, so the system has become stable. Now we can see that the at the operating gap 16 millimeter it was predicted to be levitated. Now experimental it came 13 millimeter, so obviously the operating current also will decrease. A flat plate it was predicted was 8 millimeter, from the inductance plot we choose 8 millimeters is the operating gap, a stable operating point, uh, and experimentally it came as 9 millimeter. Okay. uh, so obviously operating current also decreases 0.7 ampere to 0.64 ampere. Same case also C-shape object also predicted operating gap was 8 millimeter, experimentally it came as 9 millimeter. So predicted 0.8 ampere and experimental 0.7 ampere. So this parameter uncertainty it is sorry, this experimental errors it is coming due to the parameter uncertainty. So though we have designed, though we have taken care of all the precautions, safety disturbances we have taken, still there have some parameter uncertainty because we have checked all the parameters through three processes. One was analytical model, second was practical, and third was simulation. So that plots were actually absolutely matches to it, each and everyone, but still there have some parameter uncertainty issues is coming at the output side. So this type of parameter uncertainty, whatever ways we try to minimize the error, parameter uncertainty will be a few parameter something parameter uncertainty will come, because the system actually to make a system fully robust is very difficult to make the system fully robust. So there have some processes, advanced control strategies, robust controller, etc., that can avoid this problem. So parameter uncertainty issues is coming here, though the system has become stable, but it is not at the desired point. So some parameter variations, uncertainty is coming at the output end. Now I will discuss one important conclusion, that in attraction type levitation, and where a force is inversely proportional with the air gap. Okay, it's a open loop unstable system because one force is in the upward direction and the gravitational mg is in downward direction, so it's an unstable system. But in repulsion type levitation, mg is in the downward directions. Okay, and okay, mg is in the downward direction, and the coil force is also in the downward direction. So mg is in the downward direction, and gravitational force is also in the downward direction. So in repulsion type levitation, it's open loop stable system. In repulsion type levitation, it's an open loop stable system. That is the difference between and so actually it helps in so repulsion type levitation is easier than attraction type levitation, because open loop unstable system helps to design the controller, etc. Okay, it will help. Now again I am going to another slide. So conclusions, design and complete fabrication of a novel weighted analog controller based attraction type limitation prototype I discussed right now. So novel weighted analog controller based means that we have used a weighted gain combination approach in feedback. As already I told you that in the for the flat plate there have need to xy direction xyz direction control. So we have put all the sensors in x, y and z, and we have made a operating gap, and at that operating gap, so we have taken care of all the feedback, and we have combined it using adder. Okay, and then we have used weighted gain combination approach, and then we have feed through feedback. Okay, That is the weighted gain combination of approach. So field analysis, electromagnetic analysis, we have done through FEM packages like ANSYS, Maxwell, etc. Now I will go to a large rectangular platform levitation. Okay, a large rectangular platform levitation where four plate will be placed at a aluminum made mm, plate at four corner. The four plate will be placed at four corner of aluminum plate, and then whole body will have to levitate. So at that case, so as four plates are there, so four separate steel plates are there, we require four independent controller. So four independent controllers we require, four independent feedback we require, so each and everything is four. So for that case, we'll have to taken care of many things actually, because the platform is big, huh? So platform is big, so there are possibility of inductance variations or air gap variations, weight distribution should not be proper. This type of problem uh, will arises here. And one more thing, okay, so this you can see figure number 144. The four steel plate are placed on a bakelite sheet. Okay, bakelite sheet, and four independent coils are there. So four independent, you can say four independent setups are put together actually. Okay, so before that, what we have done, now we have combined with four individual coils and objects. Now whole platform will have to levitate. So here three things will come. The air gap variations can vary from corner to corner. That will make the system unstable. And second, weight distribution should not be proper in all the corners. So it will make the system unstable. Inductance variations also cannot be same at each corner. That will also make the system stable. So for this setup, we also need spirit level accuracy with respect to the surface of the earth. If they have spirit level accuracy in the supporting frame, and then they have a chance to minimize these problems. Okay, so we'll have to keep the object also at spirit level, and we'll have to keep the setup also in spirit level. Then only we can avoid these problems. Now before in the previous two setups, we discussed many things, and the driving circuit was transistor based. There transistor was operating as a linear amplifier. Okay, and but here we will use MOSFET. We will use the Park converter, because here more power is required, because the platform weight is more. Okay, so we require more current, and we will use duty ratio control. So this is only difference. So transistor was operating as a linear amplifier. Now MOSFET will operate as a switching devices. So this is the difference of this setup with the previous two. Now figure 145, you can see FEM analysis of the setup. FEM analysis of the setup, you can see that the flux lines are distributed, how the flux lines are exiting and entering, exiting from the core and entering on the object. So for independent coil and object is there, and you can see the core is C type and object is also C type. Okay, C type plate are placed. So for C type plate, now you can see that each and every coil is getting closed path. Okay, I have told that for the spherical object, the supporting frame of the setup also was still to get the closed path, because flux is exiting from the core and then passing through the ball, and then it is passing through the frame. But here there have no required of steel frame. we will try to make it in aluminum based frame. Means the setup would be aluminum, and these are covalent object only. So we will make the true mechanical zero setup and spirit level accuracy setup. So we will fabricate the setup uh, by aluminum such that no flux can enter from the outside and cannot make the system unstable. So you can see this the object dimensions, and C-type core is used for the coil. Okay, so it's a CRGO core and dimension is shown here. Okay, now for this setup also we require parameterization, modeling and stability analysis, controller design and feedback sensing, a buck converter, experimental waveforms. So for parameterization we require ANSYS Maxwell software for simulation electromagnetic analysis, and for modeling and stability analysis we require MATLAB, Simulink and Scilab. For controller design and feedback sensing, we require PSpice and SQL. And for PCB design, we require Express PCB. These softwares also we required for this setup also. Okay, experimental waveforms. Now, same way we will see the parameters using electromagnetic analysis, and we will say check the force air gap profile. Here one more thing will come, that whole platform is moving, so x direction, y direction force also we'll have to check. We'll have to check the fx and fy of the full platform. Okay, full platform, the force of the full platform in x direction and y direction also we'll have to check. And in this case also there will be on restoring force, like the previous case. Here also restoring force will exist in x direction and y direction. So after there have a limitation of the restoring force. So if you give a disturbance at some certain limit, then it will restore at the operating point, but after that it will goes away from the operating point. So this restoring force also exists for this setup also, and we have observed that the force fz for force versus air gap profile in z direction, force versus fz, and force in x direction, force in y direction we have also plotted through electromagnetic FEM analysis. These are important to get the practical parameters actually. So parameters, for parameter evaluation or estimations we require these plots, and we'll have to test these plots if it is coming, because they are in real time, and they are have difference between the practical plots. So sorry, simulation plots. So simulation and practical, they are have difference in real time. So how much errors is coming in simulation? So it doesn't mean that simulation and what plots we are getting, it will come in practicals. Oh, there will be some errors between simulation and practical parameters. Simulation is doing some mathematics, but practical is practical means there have lots of constants, there are some hidden problems are there. I told you that in that experimental parameters, we observed that what was our operating point, what we have chosen the operating point, that is not coming in the output. So the parameter uncertainty issue is coming. Okay, so that parameter uncertainty is coming because of the few hidden problems. Okay, hidden parts are there in the system. So hidden parts may be in design, hidden parts may be in the stability, hidden parts may be modeling, hidden parts may be fabrication, hidden parts may be stability analysis, hidden part may be manufacturing, Hidden part may be the coil. Part may be in the feedback. So we don't know where exactly the parameter uncertainty is coming. Okay, we have tried our best, but still there will be some parameter uncertainty that sometimes that cannot be predicted or identified. And for that parameter uncertainty, we record fine tuning at the end. At the end, when everything is completed, circuit fabrication is completed and it is tested, now we required, in the testing time, we required to do fine tuning to avoid the parameter uncertainty problems. Okay, so fine tuning is very very important at the end. When everything is completed, testing is going on. At that time we didn't need fine tuning using pot variable resistance, and we'll have to do fine tuning and we will make the system stable. We are doing fine tuning because of that parameter uncertainty. The parameter uncertainty is coming, so we'll have to do fine tuning. So we don't know from where the parameter uncertainty exactly it is coming, because there have lots of steps from design to fabrication. So from electrical point of view also it can come, from mechanical point of view also it can come. So it can come from the design, modeling, stability analysis, fabrications, coil design, stability analysis, circuit design, PCBs, from anywhere, uh, electrical and mechanical, it can arise. So that to avoid this parameter uncertainty, we require the fine tuning using potential resistance. What? So here you can see the block diagram. The inner loop there have a P controller and buck converter. Okay, so current feedback gain, and outer loop there have a lead compensators. So outer loop the position sensor is there, and inner loop current sensor is there. So position sensor there have a feedback gain that we can get the from the sensitivity of the sensor. So reference is voltage with respect to position. Okay, so V voltage, V per millimeter or V per meter SI unit, and then we will get the will error will be generated and lead compensator will compensate. Now you see that inner loop should be faster than the outer loop. Okay, the frequency, here frequency plays an important role. So we have chosen the frequency of the buck converter is 1 kilohertz. Okay, so uh, there have some pot we can vary the frequency and duty ratio. So you can see that inner loop response would be faster than the outer loop. So this is also an important role, because inner loop will act actually is the actuator actually. Okay, so in inner loop the actuator is there. Actuator is there in the inner loop, so actuator should be faster. So inner loop should be faster than the outer loop. Okay, now I will discuss about the uh, mm, okay, I will discuss about the waveforms. Okay, so these are the logic pulses. You can see that the mhm, logic pulse is generated using triple five timer. Okay, a gate pulses is shown, and coil current, stable coil current. So these are the simulation result using PSpice. And figure 154 also shown that logic pulse, gate pulses, and coil current. So this is the figure 153 is for coil 1, figure 15 for coil 2. Same way there have results for figure 3 and figure 4. So four independent controllers are used, so four independent results also will get. but we'll have to keep in mind that all will be synchronized at the same time. All coil should give same current at same time, means all the coils are synchronized at each and every time, otherwise it will make the system unstable. Now you can see the logic pulses. This is the experimental waveforms. Okay, so figure 155 logic pulses, figure 156 gate pulses. Okay, uh, now please see the full prototype. The full four coil is there, four independent controller are there, four independent feedback are there, and figure 158 shows that the full PCB. Okay, PCB can avoid many electrical noise or disturbances. So PCB is the best. Sometimes there will be some disconnected connectivity of the wires also occur. That type of problem we can avoid through PCB. This is a double layer PCB, and this PCB, before going to fabricate the PCB, we require to draw the drawing. Okay, through Express PCB software. So conclusion, we can say that the design complete fabrication of novel analog controller based attraction type levitation prototype we discussed. We have discussed FEM analysis using FEM packages, and we have discussed feedback control strategies using weighted gain combination of approach. So feedback sensors are combined and it has been used weighted gain combination approach. So in today's lectures we discussed about the difference between the flat plate and C-type plate. Same coil, same mass, but the shape is flat and C. So each and everything has changed because the flux pattern has changed, the inductance profile is changed, current air gap profile changed, so all the parameters have changed. So when all the parameters have changed, then obviously the modeling has been changed, stability analysis has changed, controller has been changed, and then full prototype have been changed. So from where we started, we are going there. Okay, so we started here. So flat plate and C-type plate. So analytical, before going to that, we have missed one thing, that is this please see, flat in analytical modeling also there are lots of different, because the shape is changed, shape of the object is changed, so in analytical model also is changed. You can see that for the flat plate there have 6 zones, but for the C-type plate there are 9 zones. So using Pohl's method, Pohl's method, electromagnetic analysis. So using Pohl's method, we can do integration, and we can calculate the cross-sectional area of the flux lines. And if we get the cross-sectional area of the flux lines, we can easily get the inductance. Inductance is nothing but the mu naught n square A by Z. Mu naught is the permeability, Z n is the number of turns, A is the cross sectional area, Z is the air gap. Okay, so by if we get the cross sectional area of the flux line, so we can easily get the inductance. If we get the inductance, then we will get the force. So all the parameters we will get from the analytical model. Analytical model is based on mathematics, and we will check these plots with the simulation and experimental also, and then we will take the parameters at the particular operating point. Okay, at the particular operating point we will take the at particular operating gap we will take the operating points, and then we will put all the parameters in the small signal model, and then we will get the transfer function, and then stability analysis will start. Okay, then after modeling, if modeling is completed, then we can go for the stability analysis, and we can check the controller which type of controller is perfect for the system. That the analysis we can do using MATLAB, Simulink at Scilab. Once controller has been designed, then we have to go for the fabrication. And then if fabrication is done through Vero board, fast breadboard and then Vero board, if it is working properly, then we can go for the PCB design. Before going to the PCB design, we'll have to make the drawing in Express PCB software, and then we'll have to decide that it will be 2 layer, 4 layer, uh, something. We'll have to decide, and then we'll test the circuits in the practical setup. After testing the circuits, if it is okay, then we will fix the PCB in the with the setup, and then it will be completed. So next session, and I will discuss on circuit design and circuit fabrication in next session is very much important, because still till now what we have discussed, that is the design, stability analysis, 80-90% are related to fabrication. Okay, now we will go in the next session. Next session we will go the practical circuit fabrication and testing of the associated circuits. That is very important part. Okay, because there have lots of parameter uncertainty, robustness issues will come. That we will see in the next session. Thank you. Okay.